Hello everybody. In this video we're going to start the seventh chapter in the textbook, which is entitled the Dimensional Analysis and Modeling. This chapter is covered in, or the contents of this chapter are covered in, or we cover them in different courses. We cover them in heat and fluid mechanics, and in heat transfer, and in mass transfer. And it might be covered in other courses like reaction engineering, for example. And the reason is that despite having or the different topics covered in these courses, but the concept that we cover here is common in these different fields of engineering, and that's why it's important to understand it well. Because it's very helpful. It's going to be very useful in this course, as it introduces some concepts that we will use in the next chapter, which is chapter 8. And in general gives some very useful information, although we don't have here like a lot of problems that we will solve and different things. It's just a procedure that we will follow at the end, but it's very useful to understand why we follow this procedure and why we do this dimensional analysis. So to start, we will start with a very basic concept to review this concept, which is the difference between units and dimensions. So units and dimensions are two different terms that represent two different concepts. The first is the dimension. So any quantity will have a dimension. So the length is a measurable quantity. So it has it's a length. The way we express it is based on the units that we use. So if we have units of, if we have length, we can express it in units of meter, centimeter, foot. All of them are different units for the same dimension. Okay, the same for time, for mass, for temperature. So these are all dimensions. Each one of them can be expressed using different units. All the units will have the same dimensions, of course. This is the thing. We can have dimensions of complex or compound dimensions, like the volume is L power 3, so it's a basic dimension that is raised to a power or multiplied or divided by another dimension, like the velocity, it's Lt power minus 1, then Cm L power minus 3, and so on. So this is one thing that we need to keep in mind. So the units and dimensions are something that we covered in the introduction to mass balance, so this should be a very well-known thing. The second thing here is a law that's called the law of dimensional homogeneity, and it's a very well-known law. It states that any two terms can be added if they or they must have the same dimensions to be added. We cannot add, for instance, we cannot add mass to time, we cannot add length to force, so the two terms must have the same dimensions. And one example is Bernoulli equation that we used before, and you can apply it to any equation that we use. So despite having the three terms composed of different variables, but the analysis of the dimensions will lead to the same dimension for all of them, which is ml squared t power minus 3. So this is the law of dimensional homogeneity, and by the way, this is one of the easy ways of checking the equations, because it's one of the checks or the conditions for an equation to be a valid equation. Okay, so now let's move to the next point, which is the non-dimensional quantities. So we have quantities that can be expressed in dimensional forms and non-dimensional forms, and the one example that we'll see here is the concentration. So concentration can be expressed in molar concentration, which is moles per unit volume, mass concentration, which is mass per unit volume, molality, which is moles per unit mass, or mole fraction and mass fraction. The unique thing or the special thing about the mole fraction mass fraction is that both are ratios of two different or two similar quantities. I'm sorry, two similar dimensions. So they are dimensionless. So you define the mole fraction by just the number without any units. And this is something that we see a lot. And for instance, you see we defined before the specific gravity, which is a dimensionless density. We defined the efficiency, which is a dimensionless term that represents how well the pump or a turbine is performing. So we see them a lot. But the point here now is that sometimes we prefer to go for or use the dimensionless quantities more than the dimensional ones. And this is for many reasons. Actually, there are many advantages of using the dimensionless quantities. The first is that it's only defined by the quantity. As I just said, that the mole fraction is a mole fraction. It's defined only by the number. So if you know that the mole fraction is 0.25, you don't need to know anything else. It's only defined by the quantity. Okay, so I mean, this is in contrast to the rest of the dimensional quantities. If I tell you that the concentration is 1, what 1 is? It 1 mole per liter? It's 1 mole per meter cube? Is it 1 pound mole per foot cube? It's not fully defined by just the number, so, or by the quantity. So you have to define it by two pieces of information: the quantity and the units. But the dimensionless quantities, it's only defined by only one thing, which is the quantity. The second is that the value is not dependent on the unit system. For instance, if I have, for example, a length of 1 kilometer, then if I express it in meters, it's 1000. So the quantity itself, or the value, the quantity itself differs. Okay. While for the dimensionless quantities, whether you use the SI units, the US units, the CJS units, mole fraction is a mole fraction. Specific gravity is a specific gravity, regardless the type of unit system you're using. The third is a very, very interesting point here, that it for the mole fractions, I mean for the dimensionless quantities, they are, most of them, they have a very, very limited range that they cannot exceed. For mole fractions, for instance, it's from 0 to 1, or they have a much smaller range of values than the actual dimensional quantities. For instance, the range of values of a specific gravity is much less than the range of values of the density. The density can go from 1 to the maximum we know is the for liquids, I mean, is the mercury. It's 13,000. Okay, while the specific gravity ranges from point something to 13.6. So the window is much narrower than the window that is huge for the actual density. And this is very useful for many reasons. The first is for cases that we are doing iterative solution, meaning that we are solving by trial and error. We assume a value and then we recalculate it. So the solution can be converting or convert quicker if you assume a value that is closer to the final answer. Okay, so I don't know the final answer, I don't know the solution, but if I assume a value that's closer to the solution, I will take less time and less trials to reach the correct answer. And the dimensionless quantities will give us a very good opportunity to do this, because you have a very wide, narrow range. For instance, if you have a mole fraction, it's from 0 to 1. Whatever you assume is going to be close to the answer. Okay, so it makes the calculations quicker, the assumptions more realistic in case of iterative solutions. One more advantage is that having this limited range gives you a good way of evaluating the solutions that you get, if they're logical or not. For instance, if you do calculations and calculate the mole fraction and you find it to be let's say 1.5, without hesitation, you would know that this is not correct, that there is something wrong with your calculations. The mole fraction can never be more than 1. If you calculate it and find it to be negative, it's definitely wrong because it cannot be less than 0. When you have this limited range, it gives you a good way of evaluating the answers, which is not as easy in case of dimensional quantities. The last point, which is a very important point and very important advantage of the dimensionless quantities, is that they give us a physical meaning. They have a physical meaning. They give us some information, some very useful information about the system that we are dealing with. We will see this in details in the coming example, or in the coming videos and the next chapter. But this is a very important thing. You can imagine that you can calculate a dimensionless quantity, and by just knowing the number, you can know very important information about the system. By just calculating one number, you can know very important and critical information about the system, which is something that you cannot get by using the regular dimensional quantities. So this is what we need to discuss here. I'll stop here, and in the next video, inshallah, we are going to take this dimensionless or the advantage of dimensionless quantities to a next level by applying this to equations, and see if we have an equation, what are the advantages of converting this whole equation into a dimensionless equation. This is also, there are more advantages that we will see inshallah in the next time. So I'll see you then. Goodbye.